This is a test, an introduction to property-based testing with hypothesis. I'm Noah Seger. You can find me these places. I work at Condé Nast. We publish a lot of magazines, decreasingly in print and increasingly on the internet. Everything from Pitchfork to the New Yorker to Allure. That's my name with the accent. That's my name with New Yorker-style diacritics. So I want to start with an affirmation. Testing is a design tool. So you don't have to believe it, but I think you should just try saying it out loud and see if you observe any truth in those words. So I'm going to say it one more time, no pressure. You can say it with me or not. Testing is a design tool. It feels really good. Thanks. So Travis was talking about the value of studying religion yesterday, so I think we should look at the creator of a religion called Testdriven development for some guidance. Kent Beck said this. So we get paid for code that works, not for tests. So tests are a great tool, but we want to really minimize our time we spend there. So I really want you to get two things out of this talk, actually. And the first thing is that the more thought you put into your tests, the less fear you're going to have, and the higher quality code you're going to have. Okay, and the second very practical thing is that everybody here should install Hypothesis at the end of this talk. So it's a testing tool. You can find it on the web at these URLs. And it's a tool for doing property-based testing specifically. It works both in unit test and PyTest, and anywhere you're using fixture data today, you can actually just probably drop this in and replace fixtures with Hypothesis. So that's one level that it works at. But what is a property? This, phrased another way, is what should hold true about your code no matter what. Think in terms of invariance. No matter what changes, the inputs or the outputs, these properties about your code should always be the same. And I think a lot of times you'll hear these math terms come into it when you do property-based testing. So drawing from math, all functions have two properties. They have a domain, which values we draw from, and range, which values our function produces. And I think a lot of times when we write example-based tests, we have this kind of nonsensical Euclidean space that looks like this, right? It's one point, one test case, it worked, and okay, we call it done. But with Hypothesis, we have a space that looks more like this. These are just made up dots, but we see that nothing's good before zero. Things are mostly good above it, but some things aren't, right? And then just, I think I have a bonus picture here of when you have no tests. It's like that. So let's avoid that. We can use a standard approach for testing properties that looks something like this. First, we're going to define the properties of the function. We're going to use hypothesis strategies to generate the inputs for the function. And then Hypothesis is going to do that last part for us and find a minimal bad example of where our code breaks. And just as an aside, I'm giving you a framework here, but just be skeptical of frameworks in general. Just install it and see what you can get out of it. So here's the canonical example. We're going to define a property here for encode and decode. This is like the ultimate property-based testing freebie. Like anytime you see this symmetry where everything you encode should be decoded to the same thing, then like throwing property-based testing at it is going to work really well. So that's the assertion, right? Decode of encode of a string is the same string. So the same thing should be encoding, decoding, buffer should be the same string. That's the assertion we set up. That's the property of the code. And then you can see this given decorator. Well, maybe you can't. That's like barely visible, isn't it? So it's given all text. So Hypothesis has this strategy called text, and it's going to generate every conceivable string for us. Not just strings. This is a bunch of stuff you can do with Hypothesis. You can generate integers. You can generate text. You can use union operators to combine all those things. So like here we're defining numbers to be either integers or decimals or floats. And then we can just say, give us an example. And that's where you would be using it in place of fixtures that you have right now. And then you can compose those strategies into nested strategies. So at the bottom you see strategies.lists. So that's creating lists of numbers. Any kind of list of numbers. Empty lists like 1, 1.23, decimal 1.0, all in the same list. So like just as a quick example, let's check in. We're asking hypothesis for examples of this. Like just what would you choose if you had to create an integer? Like throw out a number that you would actually likely use in your test case.
1, 0.
All right, this is what hypothesis thinks of first. I can't even read that. So like the text it gives you is the Unicode ranges that you didn't know existed. Here we're saying like, I expect my URLs to look something like this, and hypothesis is like, oh, really, like this? I did say that there would be some Django, so I just want to show you an example from the documentation. Hypothesis is just zagging all the time. So we have like a customer object. All we just say is, hey, just give us a customer, and it makes it up for you. So if you are writing Django today and you are doing a lot of manual effort to set up your test fixtures doing this stuff, then this is a big win. This is less code than Factory Boy. I don't know, does anybody here use Factory Boy for test fixtures right now? It's cool, but this is easier, and it's going to give you a lot more confidence at the end of the day, I think. Just a quick list. We can do all this stuff. Like, I just want to say dates, right? If you're just saying, like, if you have a hard-coded date in your test, you should be a lot more scared than you are right now. Let's look at like a more concrete example here. So splitting a tab. This is something I know a little bit about from a past life at Tabbed Out. So we're saying that given some total and n number of people in the party, we want everybody to pay the same amount at the end, and we're going to give you a list back of the amount that each person should pay. So this is the naive way to do it. We just say the amount each person pays is the total divided by the number of people. And then we're going to write a property for that in using hypothesis. We say that we split the check, and then our property is that when we sum each portion of the check again, that should always be the same as the original check total, right? Because you don't want to leave any remainder on the check. And then we set up a few like constraints. We want to say that our integer strategy always has to start at 1 because we never want 0 people splitting the tab. And we want to say that our check total has to be 0 or more because I guess you can split at 0. I don't know what that means, but we don't want to allow an infinite tab, and we don't want an invalid dollar amount, like not a number, and we want to use $2 places or two places for the decimal so that we have pennies. Yeah, so when we run this test, hypothesis punches us in the face and says that this particular case failed. So decimal 0.339999, right? Like that's what we got back when we checked our property. It does not equal the check total of 34 cents. And it gives you a falsifying example at the top here. So it says, when we had a check total of 34 cents and we had 3 people in the party, then this is the bad result we got. Okay, so let's take that information. We can kind of see like we should really not have these fractions of pennies in our code, so we need to fix that. And we come back and we say, all right, we're going to round the subtotal to the nearest 2 decimal places, so we have pennies. Okay. We throw that back at hypothesis, and it's like, no, still no. When we had a check total of 25 cents, we had 2 people. You can't split that evenly, so you ended up with 24 cents again because we rounded it down, and you left a penny on the tab. So then we go back and finally do it the right way, and we check for the remainder at the end, and we just give somebody, like the unlucky last member of the party, that penny. And that's somebody has to end up with that. and success, right? Hypothesis is good with this. And we can be pretty sure that like it checked our entire range because it's going to do 100 examples at a minimum and like split that space to smaller and smaller degrees and until it can't really find anything. So yeah, now we are pretty confident that we have a function that can handle splitting a check up to 10 septillion dollars, which is when you run out of decimal precision by default in Python. Okay, so that's the more practical stuff. I just have a demo, I guess, we can try. It's not like the most realistic example, but maybe it's fun. I'm calling it my hit game Propemon. So let's see if we can battle some monsters. Find the plus. Okay. This is extremely illegible, isn't it? So can anybody read that at all? Kind of ish. Let me let me walk through it just a little bit, like how we're setting up. Beyond just generic strategies, Hypothesis gives you these like state machines that you can build to run stateful systems. And so kind of the system I've set up here is that we have a few different monsters in our roster. And at each step, they're going to fight each other. And then at the end, we want to validate some properties about our system. Like we want to make sure that this is a zero-sum game, so for everybody who wins, there has to be a loser, right? So the total number of wins minus the total number of losses is 0. And then I've set up this awesome elemental fighting system where each kind can beat other kinds. And so I want to make sure that we never have a winner who unexpectedly beat the element who's super effective against them. And then, so I'm going to run it, and Hypothesis is going to do a lot of fighting and then a lot of validating, and at the end it's going to say, oh, yeah, nothing went wrong. Whereas I can introduce a quick bug here. I have no idea if this will work. Yeah. So it's telling me that electric should never have beat rock, and it exposed my bug right away. So let's get back to the presentation. Definitely keep an eye out for this game, please. Okay, so I want to leave you with this quote about designing properties as kind of the intended function of the code. This is a quote from a book called Toward Zero Defect Programming, and is highlighted by Michael Feathers in like a talk he did late last year. So they're talking about this process of before they started designing the code, writing out what they intended it to do. So if you did this, right, you don't even really need to like look at the code if you're comfortable. So they found that experienced programmers would probably do these things up front. So think about it before you do it. And using this process, they ended up with something like four or 5 defects per 1,000 lines of code. So I want to encourage you to use properties to design. I think it can make our code clearer, more robust, easier to change. Thank you. Think about your tests and just install Hypothesis. There's no reason not to. We have a couple of minutes for questions, I guess. Okay. Anybody have a question? Yeah.
So you said Hypothesis runs through a lot of different options, but it clearly can't run through every possible option because how many does it actually try? Like, is it those and are those kind of equal?
Yeah, so yes. So does hypothesis try everything? No, it doesn't. How much does it try? By default, 100 things. And how it splits that space is not totally clear to me, but I know that it's going to try like long strings and short strings. It's going to try high numbers and low numbers. And it's going to also do some kind of like unexpected clustery things with randomness, like generate a whole bunch of the same object together sometimes when you decide to sample stuff. Just because I saw that, I was trying to figure out why my simulation wasn't working, and it was because it was fighting like all fire propamon against each other, and those properties didn't hold. Yep.
So, is it deterministic? I mean, if you run the same test twice, is it possible to pass and then fail?
It is possible. So is it deterministic? Can it run the? Can it? That's the question, I think, right? Does it fail the same way twice if you run it twice in a row? Is that the question?
Well, could it pass in one test just by luck and then fail on a second pass?
Okay, so can it pass by luck the first time and then fail on a second pass? It gives you there's two facilities for this actually. The first one you can see in this slide. If you add the seed property to your test, then it's going to run the same way every time and actually be deterministic. And then the second thing it does is it keeps a database in .hypothesis in the root of your project. So failures are deterministic after their first encounter.
Is that something version control, or is it expected to?
So
do you keep that persistent?
should we version control our failure database? I don't think so. I think that's a tool you would use in development. Nose tests can do the same thing, I think, and like keep databases of your failures so that you run into them again, and you can rerun failed tests. I wouldn't do it, but you can also take a failure and then you can use add example and decorate your test function with that, and then that example will always be run, no matter what else it tries in the range. Anything else? Sure.
So there were some suites of strategies there that are built in. Does it have, or are there people who built extensions for tables that have to do with properties?
Yeah, so there's a first-party, sorry, I did blow through this slide, but there's a first-party extension for NumPy arrays, first-party extension for Django models, third-party extension for faker data, and yeah, you can plug in whatever strategy you need to build something. If you use Python 3 type annotation, it'll also infer those automatically for you with like the build strategy. So.
You write dates with an exclamation mark. One, what you consider by default well-known weird date attributes like leap years, things like a lot of times in history or etc.
Yeah, so does it include weird edge cases? Yeah, so the search space is all dates and times, so it's going to try to find a bunch of weird stuff, I'm sure. Yeah. Has anyone ever had like a test failure that only happens after 5 p.m. or something? So hopefully 5 p.m. can be whenever now and not just at 5 p.m. Okay, I think we're out of time, so thanks, and I can talk about it to anybody else in the hallway.